Today's session is about analog filters using low pass prototype transformation. Or we can say the another heading for this topic is analog to analog frequency transformations. So what it means? What is the meaning of analog to analog frequency transformations? Uh, as per the title, here also analog frequency is there. How we are converting a analog frequency to another analog frequency. So, what is meant by prototype? All these key factors, parameters, we will discuss in the today's session. First, this method, nothing but analog filters using low-pass prototype transformation. This method converts the analog low-pass filter with cutoff frequency 1 radians per second. This point you have to remember. Frequency transformation. Low-pass prototype transformation means analog filters using low-pass filter or prototype transformation means converts the analog low-pass filter with cutoff frequency 1 radians per second. If the cutoff frequency is 1 radians per second, that kind of low-pass filters are called as prototype low-pass filters. So these low-pass prototype filters are converted to other analog filters like low-pass filter, high-pass filter, band-pass filter, and band-stop filters with their frequency specifications. Okay. First, we will see prototype, or we can say normalized. Normalized means cutoff frequency is 1 radians per second. First, we will see the first case normalized low-pass filter to low-pass filter of desired frequency. How we are converting this prototype low pass filter, or we can say normalized low pass filter to LPF of desired frequency. Let us say H of S denote the transfer function of a low pass filter with passband edge frequency omega p. Omega P stands for passband, omega stands for frequency. So this is called as omega p is called as passband edge frequency is 1 radians per second. As I told, passband edge, or we can say cutoff frequency. Cutoff frequency is 1 radians per second. That type of filter is called as low pass prototype filter, or we can say normalized low pass filter. So this filter is known as analog low pass normalized filter. This filter is called as a filter having cutoff frequency 1 radians per second, or we can say passband edge frequency omega p equal to 1 radians per second. This type of filter is known as analog low pass normalized filter, or we can say analog low pass prototype filter. Okay. If omega u upper band, omega stands for is the desired passband edge frequency of the new low pass filter. What it is written here? If omega u is the desired passband edge frequency of the new low pass filter, then transfer function of this new low pass filter is obtained by using the transformation wherever s is there in the transfer function. Transfer function is written as we know h of s. The transfer function of the filter, how we are writing? We are writing like this. This is the transfer function. H of s is what? H of s indicates the transfer function of the filter. So this S is replaced by what? S is replaced by S divided by omega u. Okay. In some other textbooks, we can written as this is replaced by, this is written as S is replaced by S by omega c, where omega c stands for cutoff frequency. So cutoff frequency. So from this expression, we can say that prototype low pass filter is converted to low pass filter of desired frequency. That is done by wherever s is there in the transfer function of the filter, that s is replaced by s divided by omega c, or where omega c stands for cutoff frequency of the filter. Or we can write expression like this: s divided by omega u. Meaning is same. Okay, where arrow mark indicates that is read as replaced by. S is here arrow mark. We are reading this arrow mark as S is replaced by S by omega u, or we can write S by omega c. So if you are seeing this one in terms of diagram, Okay, before seeing in type of characteristics, let us see what we are doing. H dash of S be the transfer function of the new low pass filter. H of S is what? H of S is the transfer function of the prototype filter. H of S is what? H of S is, it is the transfer function of the prototype filter or normalized filter. That is, wherever S is there, that S is replaced by S by omega C or S by omega U. Then what we are getting? We are getting H dash of S. And we are getting H dash of S. Nothing but H of S by omega C. Or we can write H of S by omega U. So this is, sorry, this is called as what? It is the H dash of S is it is the transfer function of new low pass filter of desired frequency. Okay, is it clear? H dash of S is what? It is the transfer function of the new low pass filter of desired frequency. So if we are seeing this one in terms of expression, H dash of S be the transfer function of the new low pass filter, then H dash of S equal to H of S. Wherever S is there, S is replaced by S by omega U or S by omega C. So hence H dash of S is equal to H of S divided by omega U, or we can write S divided by omega C. Here we have translated the cutoff frequency from 1 radians per second to omega U radians per second, or we can say WC radians per second. Thus, it justifies the correctness of the normalized low pass filter to low pass transformation. So what we did here from this expression, what we did here, what we got? So we got that normalized low pass filter is transferred to low pass filter of desired frequency. So let us see this function, this operation in terms of diagram. So if I am representing characteristics, this is what? This is the HP of S. Okay, this is frequency component. Okay, this is 0. Now as per the normalized case, normalized, or we can say prototype analog low pass filter have the cutoff frequency, that is 1 radians per second. 1 radians per second. That is replaced by what? S is replaced by S by omega C. S by omega C, or we can write S by omega U. Then what we are getting? We are getting the characteristics like this: H dash of S and cutoff frequency becomes what? Omega C, or we can write omega U. So this is the what characteristics of the low pass filter, prototype low pass filter, or we can say normalized low pass filter that has 1 radians per second, that is replaced by S by omega C. This is also low pass filter. This is also low pass filter. The difference between these two things is that it is of prototype. It is of prototype. It is of desired frequency. It is of prototype, or we can say it is of normalized frequency, normalized low pass filter, that is transformed to desired low pass filter. So next one, similarly, we can go for next one, that is normalized low pass filter to high pass transformation. So the low pass to high pass, the normalized low pass to or prototype low pass filter to high pass transformation is simply achieved by replacing S by 1 by S. Wherever S is there, that is replaced by 1 by S. If the desired high pass filter has passband edge frequency omega U, then the transformation is wherever S is there, that S is written as omega U by S, or in other words, we can write omega C by S. So then H dash of S be the transfer function of the new high pass filter. How we are getting this H dash of S? We are getting h dash of s as h of s, wherever in the h of s, s is replaced by omega u by s, or we can write s is replaced by omega c by s. So this is the transfer function of the new high pass filter. So let us see this expression in terms of characteristics. How we are sketching? So this is normalized low pass filter. This is normalized low pass filter having the frequency 1 radians per second. This is what normalized or prototype low pass filter. What we are doing? We are transforming this low pass filter, normalized or prototype low pass filter, to high pass filter of desired frequency. High pass filter of desired frequency. So that one I'm sketching like this. Frequency characteristics of high pass filter. This is what h dash of s. This is the cutoff frequency. This becomes what? Omega c. This becomes what? Omega c. It is what? It is HPF, high pass filter of desired frequency as per the requirement. So how we are performing this one? Converting from low pass filter to high pass filter of desired frequency. Repeating once again, the conversion transformation from normalized or prototype low pass filter to high pass filter of desired frequency, that is done by wherever s is there, that is replaced by omega c by s, or we can write s equal to omega u by s, meaning is same. In some textbook this equation is referred, in some textbook this equation is referred, meaning is same. Clear? Okay, this is about what? This is about transformation from normalized or prototype low pass filter to high pass filter of desired frequency. Let's see next case. Next case is about what? A normalized low pass filter to band pass transformation. Next case is normalized low pass filter to band pass filter transformation, or we can say prototype low pass filter to band pass transformation. It is done by, for a low pass to band pass transformation, it should be understood that a band pass filter is essentially a combination of low pass filter and high pass filter. So this statement we can picturize from the frequency characteristics of band pass filter. It is a combination of both low pass as well as high pass filter. Regarding this statement, we'll discuss with the help of diagram frequency characteristics. If we want the band pass filter with higher band edge frequency of omega u and lower band edge frequency omega l, okay, then we have to apply following transformations. Of course, for the band pass filters, we are having two edges. One is higher band, another one is lower band. So those are indicated by omega u and lower is indicated by omega l. Or in other cases, we can also represent it as omega h. It is higher band frequency, higher band frequency, and omega l stands for lower band frequency. Okay, let us see the this one with the help of before that what we are doing. We are doing what? S is replaced by s square plus omega u omega l divided by s multiplied by higher band frequency minus lower band frequency, that is omega u minus omega l. Okay, let us see the diagram. So what we are doing, we are converting prototyped low pass filter or normalized low pass filter to It is what? It is normalized or prototype low pass filter that is transformed to what? Band pass. Band pass filter is a combination of low pass and high pass filter. So that one we are sketching as it is the new transfer function h dash of s. H dash of s is what we are getting. See, it is we are going to represent two band edges. This is the center frequency omega naught I will represent. This is lower edge, this is upper or higher edge. Omega stands for higher band frequency, omega stands for lower band frequency. It is center. So this is what? This is band pass frequency. This amount of frequency we are going to pass over the filter. So lower band frequency and higher band frequency. So that is done by s is replaced by s square plus omega naught square divided by sw divided by sw. You may ask one doubt. See here, sir, yeah, in the earlier case we observed this case, that is s is replaced by s square plus omega u omega l divided by s multiplied by higher band frequency minus lower band frequency. But in this case we written like this, meaning is same. Don't confuse, meaning is same. How both are same I am going to explain now. See here, I will write omega naught is equal to square root of omega h multiplied by omega l. Similarly, w is equal to higher band frequency minus lower band frequency. Now, so what about if you take the square on both sides? Omega naught square equal to what? Omega h into omega l. Okay, same thing I written here. Compare these two things. Say I told here omega u stands for omega h, omega l stands for wl, omega l. So omega, so this one we can write same thing, we can write s square plus omega h multiplied by omega l divided by s into omega h minus omega l. If omega h minus omega l is indicated as w, then denominator s multiplied by w. Okay, coming to the numerator, uh, square root of omega h multiplied by omega l is omega naught. Then take the square on both sides, we'll get what? Omega naught square equal to omega h multiplied by omega l. Hence numerator becomes s square plus omega naught square, meaning is same. This is about what? Transforming normalized low pass filter to band pass filter of desired frequency. Okay, let's move on to the next topic, that is uh, normalized low pass filter to band stop or notch transformation. Okay, how we are performing this one is simple thing. If you want to, if you want the band stop filter with higher band edge frequency of omega u and lower band edge frequency of omega l, then we have to apply the following transformation as s is replaced by s multiplied by omega u minus omega l divided by s square plus omega u into omega l. See, you can compare these two expressions. You can compare these two expressions, reciprocal of this one, correct? This expression is, this term is, it is the reciprocal of this, because band pass filter and band stop filter, you can observe the characteristics of these two filters. Both are in reverse manner. Okay, both are in reverse manner. See, then how we are writing this one? Simple thing, let us see in terms of diagram. So 1 radians per second. It is characteristics of what? Normalized or prototype low pass filter that is transformed to band stop filter h dash of s. So this is what? This is lower end frequency, lower band frequency. This is what? This is upper band frequency. This is center frequency. Okay, it is of this amount of frequency is stop. This amount of frequency is stop. So here also same thing. SC is replaced by SW divided by S square plus omega naught square. Okay, what we did here? Nothing but H dash of S. Now we are getting H of SW divided by S square plus omega naught square. Okay, likewise we are getting the, it is band stop filter of desired frequency. So from this diagram we can say that we transformed normalized or prototype low pass filter to band stop filter of desired frequency by performing S is replaced by SW divided by S square plus omega naught square. So already we know in the previous case omega naught stands for square root of omega h into omega L, or we can write omega naught square is equal to omega h into omega L, or W is equal to is what? It is the difference between the higher band frequency minus lower band frequency. Hence, the term becomes S is replaced by S omega SW divided by S square plus omega naught square. It is about what? 4 cases we discussed up to till we discussed 4 cases. Those are, I will recall. First case is what we discussed. First case, one, normalized or prototype. Remember this point, we have to remember. Normalize or prototype means the cutoff frequency is 1 radians per second. Cutoff frequency is 1 radians per second. The meaning of these two words is 1 radians per second. That is converted to what? Low pass filter. Sorry. Normalize or prototype low pass filter. Low pass filter is converted to low pass filter of desired frequency. Normalize, first case we discussed normalize or prototype low pass filter to low pass filter of desired frequency. Second case we discussed normalized or prototype low pass filter to what? High pass filter. Similarly, case number 3, normalized prototype low pass filter to what? We discussed band pass filter. So last one we discussed normalize or prototype low pass filter to band stop filter. So this is about what? Transforming analog to analog frequency transformations. Both are analog filters. So how we discuss? We discuss transformation of analog filter to other analog filters, or we can say the heading for this topic: analog filters using low pass prototype transformation. Okay. Now this is about normalized to other filters, analog filters. We will discuss vice versa. Vice versa means uh, low pass filter to what? Normalized low pass filter, high pass filter to. Now we discuss in the forward case. These are forward cases. Now we will discuss reverse cases. This is what is called as forward cases we discuss. These are called as forward transformation. or we can say these are called as forward frequency transformations. Next, we'll discuss reverse frequency transformation. Reverse frequency transformation means vice versa. Vice versa means low pass filter of desired frequency transformed back to normalized low pass filter. Next, high pass filter of desired frequency is transformed to or converted to normalized low pass filter. Similarly, band pass to low pass, normalized low pass. Last one, band stop to normalized low pass filter. So for that, we have equations that is called as backward design equations. Previous case, four equations, those are called as forward design equations. The coming four equations are called as backward design equations. So first one, low pass filter to normalized low pass filter. So it is first case is what? Low pass filter of desired frequency to normalized low pass filter, that is done by omega s is replaced by omega s dash divided by omega u. Next case, high pass filter of desired frequency to normalized low pass filter, that is done by omega s is replaced by omega u divided by omega s dash. Next case is band pass filter of desired frequency to normalized low pass filter, that is done by a equal to minus omega 1 square plus omega u omega l divided by omega 1 multiplied by omega u minus omega l. B equal to omega 2 square minus omega u into omega l divided by omega 2 multiplied by higher band frequency minus lower band frequency. Then omega s equal to, this is the last equation, final equation. With the help of this equation only, we are transforming, converting band pass to normalized low pass filter. That is, equation is omega s cutoff frequency. Omega s equal to, omega stands for cutoff frequency. Cutoff frequency of what? Normalized low pass filter. Omega is equal to minimum of these two values. Minimum of these two values. Similarly, last case, last backward design equation, that is band stop filter of desired frequency to normalized low pass filter, that is done by a equal to omega 1 multiplied by omega u minus omega l divided by minus omega 1 square plus omega u into omega l, and b equal to omega 2 multiplied by higher band frequency minus lower band frequency divided by minus omega 2 square plus omega u multiplied by omega l. Then final equation is omega s cutoff frequency equal to minimum of these two values. So we discuss forward design equations as well as backward design equations. Let us familiar about these 8 equations. We will take one example. With the help of an example, we will discuss how we are going to convert from analog to analog frequency transformation. So I will take one best example for that topic. For this topic, see here how we are performing this operation. We will see with an example. A high pass filter. See, sorry. Let h of s equal to 1 divided by s square plus s plus 1 represent the transfer function of low pass filter with a pass band of 1 radians per second. So from this statement, we can say that h of s is the transfer function of the low pass filter. H of s is what? It is the transfer function of the low pass filter, but it is of which type? It is of prototype because it has pass band frequency is 1 radians per second. So from this statement, we can say that he is given in the problem. It is given that it is a normalized low pass filter because it has pass band frequency, or we can say cutoff frequency is 1 radians per second. Because of that reason, the given transfer function h of s equal to 1 divided by s square plus s plus 1. It is the transfer function of normalized low pass filter. Fine. Next, use frequency transformations to find the transfer functions of the following analog filters. First case, a low pass filter with pass band of 10 radians per second. So what is the meaning of this first case? We have to convert this normalized low pass. This is the transfer function of normalized low pass filter. This transfer function is transformed to a low pass filter with of this frequency. So meaning normalized low pass filter is transformed to low pass filter of this frequency. Okay. Next question. Next bit. B bit. A high pass filter with cutoff frequency 1 radians per second. It means conversion from normalized low pass filter to high pass filter with this amount of frequency. C bit. A high pass filter with cutoff frequency 10 radians per second. C bit also indicates same thing. That is conversion from normalized low pass filter to high pass filter with 10 radians per second. Next. D bit, a band pass filter with a pass band of 10 radians per second and center frequency omega naught, that is indicated by omega naught, center frequency of 100 radians per second. So from this D bit we can say that it is a conversion from normalized low pass filter to band pass filter. Last one, E bit, a band stop filter with stop band of 2 radians per second and center frequency is 10 radians per second. So let us solve this example step by step, one by one. First, I will take A bit. That is, what is the A bit? In the A bit, it is a transformation from prototype low pass filter or normalized low pass filter to low pass filter transformation. So for that, S is replaced by S by omega U. Omega U stands for pass band edge frequency, or we can write S is replaced by S by omega C. We discussed already. Hence, the required low pass filter, that is H dash of S, or we can write it is new. N stands for new transfer function. Hn of S equal to H of S, wherever S is replaced by S by omega U. Omega U is what? In the first bit, it is given 10 radians per second. So in place of omega U, I substituted 10. Hence, S is replaced by S by 10. Wherever S is there in the transfer function, simply replace by S by 10. So observe here, S is replaced by S by 10 square. Next, plus S is replaced by S by 10 plus 1. Do the simplification of this one. We will get the answer as H of S. It is the transfer function of low pass filter of frequency 10 radians per second is H of S equal to 100 divided by S square plus 10S plus 100. Okay. Next, move on to the B bit. That is, B bit is what? B bit is what? A high pass filter with a cutoff frequency 1 radians per second. So for the B bit, it is the transformation from normalized low pass filter to high pass filter. For that, S is replaced by omega U by S. In this B bit, the value of omega U is given, that is 1 radians per second. Here, omega U is given 1 radians per second. Hence, what happens? The required high pass filter, now to get the required high pass filter, wherever S is there, S is replaced by omega U by S. Omega equal to what? 1 is there. So 1 by S. Okay. Sorry. Here it is there. 1 by S. Hence it becomes S square is there, that is replaced by 1 by S square, plus S is there, that is replaced by 1 by S plus 1. Do the simplification, we get the answer, that is H of S equal to S square divided by S square plus S plus 1. Clear? Here omega equal to what? 1 radians per second. Clear. Coming to the C bit, transformation from high pass, normalized low pass filter to high pass filter with 10 radians per second. Hence, here it becomes what? 10 radians per second. S is replaced by omega U by S. It is C bit. S is replaced by omega U by S. Hence, omega equal to what? 10 radians per second. So wherever s is omega is there, substitute s is replaced by 10 by s. Hence, s is replaced by 10 by s square whole square plus s is replaced by 10 by s plus 1. Do the simplification. We are getting the answer as s square plus s square divided by s square plus 10s plus 100. This is what h of s. This is the transfer function of high pass filter of frequency 10 radians per second. Next, d bit. Coming to the d bit, what is d bit? In the d bit, it is clearly mentioned that we have to convert, transform normalized low pass filter to band pass filter. He is given the specifications of pass band of 10 radians per second and center frequency is 100 radians per second. See this example. Let us see the fourth bit, d bit. Normalize low pass filter to band pass transformation. So what is the formula for that? S is replaced by s square plus omega u multiplied by omega l divided by s multiplied by omega u minus omega l. So meaning is same. In the previous cases we discussed center frequency, discussed this one. This is center frequency, correct? Here, but in the example we discussed, we written like this, omega no, omega naught. Meaning is same, both are same. Okay. Hence, center frequency omega naught equal to square root of higher or upper band frequency multiplied by lower band frequency. Omega naught equal to square root of omega u into omega l. This indicates what? Center frequency of band pass filter. Next, I will indicate one more notation. Width. Here I indicated this is as width. Because of that reason, I use the notation W. W stands for what? Width of the filter, width of the frequency. So here also same, but here I use the notation B naught. Meaning is same. W or B naught stands for width of the pass band frequency. Okay. Hence omega u minus omega l. Hence the required band pass filter is h of s equal to 1 divided by s square plus s plus 1. Here s is replaced by what? S is replaced by this much, that is s square. So already I discussed omega u multiplied by omega l. In order to get this value, we have to make this square, right? Hence it becomes omega naught square divided by s into b naught. You can use or you can use w, meaning is same. S b naught. Hence, so what is the value of center frequency? Center frequency is given, that is 10, 100. So what is the value? First we will see center frequency. Center frequency is given 100 radians per second. Center frequency is given 100 radians per second. Pass band is what? 10 radians per second. Substitute here. Hence, so omega naught equal to what? Omega naught is equal to 100 radians per second. Hence, R 10 square. Hence, omega naught square equal to 10 to the power 4. 10 to the power 4. Next, B naught is what? It is 10. The value of B naught is given, that is 10. 10 radians per second. Hence, S into 10 means it becomes 10s. So wherever s is there, that is replaced by s square plus 10 to the power 4 divided by 10s. In this expression, substitute s is replaced by this amount, then s is replaced by this amount, then plus 1. Do the simplification, you will get the answer as 100 s square divided by s to the power 4 plus 10 into s cube plus 20,100 s square plus 10 to the power 5 s, next 10 to the power 8. This is the answer for this case. Next, E bit. So E bit, I will once again go through the question. Band stop filter with stop band. Stop band means 2 radians per second and center frequency is 10 radians per second. Center frequency is 10 radians and stop band is 2 radians. These 2 points you have to remember, and this is the case for what? Converting normalized low pass filter to band stop filter. So for that we have the formula, that is normalized low pass filter to band stop transformation. So for that, S is replaced by S multiplied by omega u minus omega L divided by F square plus omega u into omega L. So this is nothing but omega u minus omega L indicated as a width, that is represented as V naught, or we can say W. Omega u multiplied by omega L, that is indicated as center frequency omega naught square. So wherever S is there, that is replaced by V naught is what? Stop band, that is 2 radians per second. Hence it becomes 2s. Center frequency is how much?